Hello. In this video, I shall summarize what we have found so far in the past few videos about the definition of a function and about the conditions for existence of the inverse function and the composite function. So starting from the definition of a function. We often think of a function as a mapping, and a mapping, if you remember, is just a formula or a rule that relates one number to another number. So if I give an example, for example, a number that relates x to, say, x squared plus 5. So a function is a kind of mapping, but not just any mapping, right? Not just any mapping. It's a mapping. With some conditions attached. It's a mapping that is that exists and that is unique. Okay, meaning that when we want to apply the mapping, we would find an answer. And that answer and that it is unique means that we would only find one answer when we do the mapping. Okay, so that exists means that we must get an answer. And if it's unique, it means that I get only one answer. Okay, now, and it's always good to, at the same time think about the reason, right? Or well, not reason, I mean as in think about counter examples. And we can think about counter examples by thinking of, say, a graph. Okay, if I imagine sketching a graph, for example, okay, so let's say I have a graph that looks like this. So when we say a mapping that exists, you can imagine that this is a mapping from x to y, and it's a mapping in the sense that if I have a value of x here, this graph gives me another value of y, like that. So what do we mean by saying that the mapping exists? It means that if I give a certain value of x, then this mapping, which can be this formula, or it can actually be a graph. This graph is also a mapping. Okay, we can also think of this graph as a mapping in the sense that if we give it a value of x, the graph would tell us a value of y. So it is a mapping. So the mapping must exist, right? In this case, we think of y as the mapping in the sense that is the answer that we get, that x maps onto. So in that case, what does it mean if we say that the answer does not exist? How can it not exist? Right? If I have an x here, then here's the answer. Why can't it exist? So it can't exist it is possible that it can't exist. Okay, let's look at how this is possible. It is possible that it can't exist if I define my domain, for example, to be from here to here. If I define this to be my domain, and the graph just goes from here to here, it doesn't actually keep going. Alright, it's just a small piece of graph. So if I define my domain to be from here to here, then you see, then what if x is here instead? What if x is here? If x is here, there's no graph above it. There's no graph above it, so we can't find y. We can't find the corresponding y. I mean, here there's a graph above it, so we can find a y. But here, there's nothing. So, if this is the domain and this is the mapping, okay, then there are certain values in the domain where the mapping does not exist. We can't get an answer. So this is our counterexample. So in other words, when we define a function like this, it's a mapping that exists and that is unique. There's actually something that goes behind the scene, and that something is the domain. It's the sneaky, hidden idea that is not often mentioned when we define a function. Okay, so to fully understand a function, we have to appreciate that there is this thing that comes with the function. So it's like part of the whole package. Okay. So now that we have a better idea about what exists mean, okay, so the word exists carries with it quite a lot of meaning. Let's have a look at unique. So what would be a counterexample? What does it mean if it is not unique? Okay, this is actually easy. This part is actually easy. Let me clear this up. Okay, x and y again. Now this time let me sketch a graph like this. Okay, let's say this is my mapping. Okay, it's a mapping in the sense that if I have an x here, then this graph tells me that gives me a value of y. It actually gives me another value of y as well. So two values. I'll call it y1 and y2. So in that sense, it's a mapping. It gives me an answer. Actually, in this case, it gives me two answers, which is fine for mapping. Doesn't matter how many answers we get. It's still a mapping. But the problem is, well, not a problem for the mapping, but this is a problem for a function, because if I have a mapping that gives me two answers, then the answer is not unique. Because unique, as I said, means that we have only one answer. Okay, so if I'm getting two answers, then it's not unique. So this is our counterexample. This is not the answer not unique for this mapping. So that's the definition of a function. Okay. Now next, let me talk about the existence condition for an inverse function. Inverse function. Now I want to talk about the condition for its existence. For it to exist. Now the condition for it to exist is that the let me recall what I said in an earlier video. Something to do with the range and the codomain. Right. The condition for it to exist is that the range must be the same as the codomain. This is the condition. Okay, completely abstract. So if you're seeing this for the first time, you have no idea what this is about. But hopefully you've already seen my earlier video on inverse function. So just to get a quick idea as to what exactly this means, once again let's use a graph to make an example. Graph here. Okay, so that's my x and y, and I have let's say I have a curve like this, and suppose that this is my domain. This is my domain, and suppose that my codomain goes from here to here. This is my codomain. Okay, so as a function is no problem. For each value of x, I can find a unique. I can find a value for y, and it's unique. Now, but if I want to turn this into, or if I want to find the inverse function of this function, okay, remember what I can do graphically. I can simply exchange the x and y, and that means flipping this graph about this diagonal line. Okay, so the domain comes down here, and codomain comes down here, and the domain goes up there. So to get the inverse function, this is what we do. Okay, we have the domain now becomes the codomain, and the codomain now becomes the domain. And my graph, which was up here, is now down here. Okay, so this point came from here. Okay, so that's supposed to be my inverse function. Alright, so inverse in the sense that if I, in the original function, if I have this value, the function will give me this value. Okay, if I have a here, this function gives me b. But in this function, if I have b, it will return me a. inverse function. But there's a problem with this inverse function, because there is this bit here in the domain. There is this bit here with no value, with no mapping. Okay, if I have a value here, there's no graph above it for me to find an answer to this function. So there are some, if I want this to be a function, the problem is that there are some values of x for which I have no answer. So in fact, this is not even a function. Okay, so if it's not a function, it can't be an inverse function, because an inverse function has to be a function. And you see the problem. Why? The problem is because there are some values of x here for which there is no graph or no mapping. And if we trace back the reason, okay, it's because my codomain, my codomain for the original function, okay, is actually wider than the range, which just goes from here to here. Right? Then it's wider than the actual values of this mapping. Alright, the actual values given by this function. So that's my range. And there wouldn't be this problem. I mean, the extra bit here comes from this extra bit here, where the extra bit of the codomain, which is not part of the range. And as I described earlier, if we can reduce the codomain, restrict the codomain so that it becomes smaller and just fits the range exactly, just become the same as the range, then this problem goes away. So that's why for an inverse function to exist, the range must be the same as the codomain. Okay. So finally, let me summarize the condition for composite function. Composite function. I'll call it, to make it easier, I'll refer to it as f gx, f of g of x. So I have these two functions that I want to talk about. And condition for it to exist. Okay. Now the condition for it to exist. Okay. Once again, let me try and recall what I said in the last one or two videos. It has something to do with how okay, we start with x, right? Then we use the gx, use the g to find an answer, and that answer must be in the domain of f for this to work, for me to get a final answer out of this composite function. Okay, so that means that the range of g must be inside the domain of f. Yes, that's it. The condition is that the range of g or gx is inside the domain of fx. Now I'm using pretty simple words to describe this, to hopefully make it easier to digest. But if we want to be very, very technical about this, instead of inside, I would use a subset of. So we think of the domain and the range as sets of things, sets of numbers. Okay. So, but in any case, the range of Gx is the allowed, is the set of values that can be given by Gx, and the set of and the domain of fx is the set of numbers that fx is allowed to take for the x. So in this case, I think it's fairly well. Once we are clear about the meanings of the range and domain, I think it's very clear that this condition has to be there, because if when you use Gx and you find an answer that is outside of the domain of fx, then surely you can't use that answer and calculate with fx anymore.